Well, we're back. We're about ready to wrap up Chapter 3. Can you believe that? Probability. One more section. The addition rule. And we've talked about probability in simple terms. We've talked about counting, conditional probability, and the multiplication rule. One thing to remember though, for the multiplication rule, you're talking about the word, you're talking about the word and. There we go. Multiplication rule, that's when you see the word and. Now we're going to talk this time about the addition rule. And as I mentioned in an earlier lecture, this is when we talk about or happening between statements. And then when we wrap this up, we'll be headed to the discrete probability distributions. Those are a lot of fun and pretty easy too. You'll like it, I think. So here's what we're going to do. We're going to talk about mutually exclusive events right off the bat, and then we'll talk about the addition rule. Okay, what is mutually exclusive? You're talking about two things. We'll just call them A and B, just generically. Mutually exclusive means they can't happen at the same time. And we've got some good examples coming up, so you'll know exactly what that means. But take some notes. It means A and B have no outcomes in common. Remember, outcomes, we're talking about simple outcomes usually, but not always. Here's a visual on that. We're talking about event A and event B. Notice they don't have any overlap at all. That means they're mutually exclusive. If all of these dots around here represent possible outcomes, and this is event A, this is event B, means they don't have any outcomes in common. On the other hand, over at this sample space, these events A and B do have events in common, right there where they intersect. Well, that gives you a little bit of an idea, but we'll get something better for you. Here's a good example. We've got two events. So event A is you're rolling one die. I guess I've got a bad picture there, but you can ignore the second one. We'll just scratch that out. We're rolling one die. Event A says you roll a 3. So you'd have something like that on the top instead of on the side. Rolling a 4 on a die. That means you'd have a 4 on the top. Not exactly this way, but you get the idea. Are they mutually exclusive? The question is also stated this way. If you roll a die, can you get a 3 and a 4 at the same time? No. They're mutually exclusive. It cannot happen at the same time. Cannot occur at the same time. Let's try another one. Event A is you're selecting a male student. Event B is you're selecting a nursing major. Can you do both at the same time? If not, that'd be mutually exclusive. So why don't you hit the pause button? Think about it for a second. Are these mutually exclusive? Well, no, because there are male nursing majors, not mutually exclusive. And the third one, how about this one? This would be good for nurses as well. You randomly select a blood donor, and event A says that person has a type O. Second, you select a female blood donor. Female blood donor. Are those mutually exclusive, or could you do them at the same time? Could you have an event that covers both those? You ready? Not mutually exclusive. You might have a female with type O blood and that would be an event A and an event B. Now we'll get to the addition rule. We've actually gotten to one of our major parts here, the addition rule. Remember, I gave you a little tip. We're talking about the word or between two statements. So look for the or. It says the probability of A or B. And you can write it like this. Same thing. The probability that events A or B will occur is. Now this one's a little bit different. Remember, for the multiplication rule, we multiplied the two probabilities. In this case, we're adding them. So think of or as suggesting we're going to add the probabilities. There's only one catch. If they're not mutually exclusive, that means when you talked about event A, you're talking about something that also could be true for event B. So you'd be adding those twice when you calculate your probability. So what you have to do is, if some part of your event matches with some part of another event, you're going to have to subtract what can happen in both events. Now, what you're going to see in a moment, though, is you're going to see a second formula. I'm going to give you a tip. It's my tip, and that is, this is the one to remember. In a second, you'll see a second one. Don't bother with that. What you need to remember is two things. Here's the formula for the probability of A or B. If they're mutually exclusive, then this is going to be a 0. So here's the second formula, but if the probability of both happening is 0, then all we have to do is add those two. Well, if you remember this first one, all you have to do is look for the possibility that they happen at the same time. And if they do, then this part right here that I'm circling will be 0, and you can drop it out. And that'll give you this same second one anyway. So remember this one. You don't need to bother with this one. And now this is tricky. Trust me. We're not going to actually do this, but this is the formula. If you have two events, you could extend this to more than two events. Any number, as a matter of fact. But it gets very complicated. Even with just 3 events, things get a little bit sticky. If you have 4 or 5, I'm not even going to show you the formula you'd have to have for that, because it's really weird. Anyway, so relax and let's move on. Well, let's try this. Remember, here's our formula. A or B. And so first of all, it's the addition rule, so you're going to be adding them. But in case these events overlap, then we're going to take away the events that you counted twice. All right, let's take a look. We've got a standard deck and 52 cards with no jokers. We want the probability that the card is a 4 or an ace. 4 or ace. Notice the or, so we're going to use the addition rule. They're mutually exclusive. If the card's a 4, it can't be an ace. If it's an ace, it can't be a 4. So those are mutually exclusive. So all you need to do is add the two probabilities. And there you go. Here's the probability of getting a 4. Here's the probability of getting an ace. And this one that I told you don't forget about, since you can't do both, this is a 0. So use this formula and you're covered either way you go. Just add those up. I would highly suggest use a calculator for this one. It's possible without, but it's not a whole lot of fun. We want some of this to be fun, right? All right, let's try another one. You roll a die. Okay, I've got a good picture this time. I've only got one die showing. What's the probability of the number on that being less than 3 or an odd number when you roll the die? So since it says or, we want the probability of, let's do it this way. Probability of number less than 3 or probability of an odd, sorry for the writing, we'll need the probability of the number being less than 3 plus the probability that what you got was an odd number, and we'll subtract, if it exists, of less than 3 and an odd one. So one of the things you might do first is, can they both happen at the same time? Well, if it looks a bit confusing, here's what you can try. There are only certain numbers that can come up, so make a list of them. You could get a 1, 2, 3, 4, 5, or a 6 when you roll the die one time. On the top, we'll say less than 3. So which ones are those? Well, I'm going to do this. Those are the numbers that would give us less than 3. On the bottom, odd. Which of these are odd? Well, there's a 1 and a 3 and a 5. That sets you up for success. So the first one, the probability of less than 3, we had 2 numbers out of the 6 plus odd. We had 3 out of the 6, and we have a possibility of the 1 happening both ways. So we're going to subtract 1 over 6 to get our final probability. They're not mutually exclusive. You can see 1 occurs for both events. So you're going to have to subtract that combo event, we'll call it, so that you don't add it twice. And there's our number. Notice this was the probability of less than 3. This one is the probability of an odd. And this is an odd that's less than 3. 0.667. Now, this just extends what you're doing. You have to think a little bit more because we're not just throwing a die. What you want this time is the probability again that the sales representative will sell between 75,000 and 124,999. Well, as we look at our chart over here, that means we're talking about 2 different areas. So if we want the probability that it's one of those, in one of those, it's going to be an OR statement. It'll be the probability of this one or this one. Can they happen at the same time? No. They're different lines. So we use the addition rule. Notice it's OR to get 75,000 to 124,999. It could be in either one of them, OR. So first event, second event, addition rule. And what do we have? You can't have your sales in there and in there at the same time. Or if you want to look over here, because that's what it came with, look in the table. Can you have that and that at the same time? No. Either it's in this area or it's in this area, not both. There is no overlap. Notice? No overlap. We're talking about even dollars. And there you go. We had 36 possibilities and 7 out of 36 for the first one, 9 out of 36 for the second one, and it's mutually exclusive. And where did I get the 7? Right here. Were you confused? Hope not. Where did we get the 9? Right here. Where did I get the 36? That's the grand total. So for the first one, 7 out of 36. Put it over here, 7 out of 36. Second one, 9 out of 36. What's in both? None. So we're not going to need to subtract anything, and there is our final probability that the monthly sales are between 75,000 and 124,999,000. Okay, we're back to the blood again. So for all you nurses or possible nurses, this is a good one. We're talking about the types of blood, and if you look down below, we've got O, A, B, or AB. We've got 4 types of blood. If you've got something else, you're probably not human. Well, let's not go there. In addition to that, though, for each one of those, if you've got type O blood, for example, make a mark there, you could be Rh positive, or you could be Rh negative. We want the probability that the donor has type O or type A. That means we're going to use the addition rule. So we need the probability of getting an O type blood plus the probability of getting an A type blood minus the probability that you have, RH. Okay. And yeah, let's go back. I have to start that again. Okay, for all you nursing people, we're going to talk about a blood one again. We want the probability that the donor has type O or A. So type O or A. That means we'll use the addition rule. So we'll need the probability of having an O type blood plus the probability of A type blood minus the probability that someone has an type O blood and type A blood at the same time. Well, let's see. O. What's the chance of having an O type blood? Well, there are 184 from our survey that had type O blood. So it'd be 184 over, and what's the grand total? 409. Right here. Now we need the probability for A, so we'll add that. The probability for A, and A, we've got a total of 164 that have type A blood over, again, the total is the same. Now, the question is, what's the probability of having type O blood and type A blood? Well, they're exclusive. They're mutually exclusive. So we're not going to be subtracting anything. And converting that to a decimal, we've got about an 85% chance of a person having type O or type A blood, according to our survey. Now let's take a different twist on it. This time we want the probability. We're going to be and RH negative. Oops, or RH negative. Got an or, so we're going to use the addition rule. For type B, so we'll have type B plus the probability of RH negative minus, if it exists, the probability that we pick someone with B and RH negative. All right, let's get to work. Probability of a B. Well, there are 45 Bs out of the 409, so 45 over 409 plus RH negative. Well, we have to go to this line. There's 65 that are RH negative out of 409, so 65 out of 409. But notice that we've added this 8 in twice. So we're going to have to subtract it out. Subtract the 8 over 409 that we added twice. Since they're not mutually exclusive, we're going to use the addition rule and we're going to be subtracting. So there's the total, and we've got a decimal with that too. How's it going so far? Not too bad, is it? So here's a list of some of those probabilities and types of probabilities. Remember the classical probability? All the outcomes have an equal chance of occurring. The empirical is when you've done an experiment with a lot of possibilities and you keep track of how many times a certain thing happened. Now, there is, remember, a third one, subjective probability. Subjective. And we're not going to consider that when we're doing addition or multiplication rules because we don't really have a good answer there. Next, remember the probabilities have to be between 0 and 1, and that's inclusive. Could be a 0, could be a 1. We use interval notation for that. If someone says the probability is 1.25, you can tell them no, that's not possible. The probability has to be between 0 and 1 inclusive. Next, complementary events. What were they? Well, they're events that are mutually exclusive, but put together, they take all the outcomes in the sample space and split them up between E and not E. Multiplication rule. If the events occur in sequence, one after the other, or just think of them as one after the other, even if you're rolling 2 dice, you could do them at the same time, but think of them as separate. It doesn't matter really. And the addition rule, remember this is and this for the addition rule is when you either specifically see the word or it's implied. All right, whether you're a football fan or not, here's a football example, but it's not too difficult. The important thing to note is that we've got a breakdown by position of the 255 players picked in the 2020 draft. Each one of those players who is selected is labeled as a wide receiver, offensive tackle, guard, and so on. Nobody is listed in 2 different categories. Now we know there can be, but We're just keeping it simple. In fact, the NFL probably likes to keep it simple too. And what we want is the probability that if we select a draft pick, they're not a running back or a wide receiver. How are we going to do that? So here are the events. One event, we're picking a running back. Second event, we pick a wide receiver. They're mutually exclusive and made that way, so the probability is the probability of a running back. There were 16, if you want to look at that again. 16 running backs. Where are they? Back here. 16 running backs. And the wide receivers, they're out here. There's 7 of those, but notice they're separate. So the probability of a running back, picking a running back is 16 over 255, all the people drafted, plus 37 wide receivers picked out of 255. Add those together, 53 out of 255, and you can change that into a decimal. Now, the thing is, we want not a running back or a wide receiver. So what we need to do is take our result from this, subtract it from 1 to get the not a running back or wide receiver. A nice twist to it. If you can get this, you're in real good shape. If you don't, watch this again. Try it the next time. Try a third time until you get it, even with the same numbers. Well, folks, that's about it. We're about ready for a test, perhaps. Or maybe we've already had one. Either way. The next thing we're going to do is we're going to talk about discrete probability distributions. And I think you'll enjoy this. We've got some good examples coming up. Until we meet again, take care and keep smiling. Bye-bye.